Okay, so this will be not much of a video. I'm really just going to read through this Unit 3 Padlet. I think maybe just hearing me describe a few things might help you understand these topics, even though, I mean, you could just kind of read it from here. So, Unit 3 was, I call it the experimental design unit because we talked about how to sample from a large population and the different ways you can do that and avoid bias and experiments or observational studies. What's the difference? How do you design one? And how do you determine whether you're looking at one or the other? So, again, the whole point of this unit was it's impossible to survey everyone. What's a sound way of gathering information that would make it a little bit more manageable that we could use that would be representative of a larger population? And that's what sampling is all about. So, again, purpose or big idea to make generalizations about a population by studying a subset or sample of it via polls, surveys, or other methods. Now, again, in general, a population is sometimes called a model, and we use parameters for that. That's when you'd see things like mu and sigma in a normal model, but your sample, you use statistics, and you'd use something like x bar or s to represent the mean and standard deviation. So that's just one example of the idea of sample and statistics. They go with the same letters, as does population and parameter, if you're ever asked about that. Now, types of samples and sampling methods. So again, just a couple basic vocab terms. Sampling frame, it says this is the list of individuals from whom the sample is drawn. That's kind of like the population, but it's almost like bigger than a sample but smaller than the population. That's what they're trying to emphasize here. Sample size is the size of the sample you take from the sampling frame or population. So I wouldn't worry too much about frame. Sample size, though, it's just the number of individuals in a particular sample. A pilot is almost like a trial run of something. A census, that would be if you could sample the entire population. Again, this is going on in the United States right now. It happens every 10 years. It's very hard to get every single person in a population to respond. It's called the census because that's what they're attempting to do, but more often than not, it's just a highly representative sample. Okay, now different types of samples. SRS or simple random sample. Basically, the definition of this, everyone, is something that is a sample that you draw from a population that has an equally likely chance of being chosen from any other group in the population. So, again, to be a simple random sample means that it can be produced equally likely, like this particular sample can be chosen in an equally likely manner no matter how many times you sample from the population. So if that didn't quite make sense, like for instance, here's a note about that. When other restrictions are present in the sampling method, if you're trying to choose an equal number of males and females, let's say, that might no longer be random, but it's still simple. So the idea of simple is just like drawing from them, not attaching some type of like technique or tool to the choosing of individuals. Random has to involve randomization, whether it be done through a random number generator or some other means. But again, to be simple and random means every potential and possible subset of your population could be chosen in an equally likely manner. All right. Now, moving on, stratified, that's when you sort of subdivide from the get go. Like maybe you are sampling freshmen and sophomores and juniors and seniors. So you would stratify and pick only from each of those unique groups in some way, shape, or form. Cluster is where you do some type of random choice in the beginning and then you survey everyone there. So maybe if you're trying to get a representative group of people at a high school, the cluster you choose, let's say it's sixth period lunch, you just choose that lunch period. There's going to be a mix of freshmen, sophomores, juniors, seniors, and you just ask as many people as you can during that one period. Convenience is not a smart method. Convenience is just when you ask individuals who are easily available. That can lead to response bias or non-response bias. So we'll talk about that. Systematic, that's when you have some type of like formula or algorithm that develops things. So you randomly choose a starting point, let's say. Like for instance, let's say you are waiting outside of the Spartan gym, and you say, starting with this person, every eighth kid, I'm going to ask them a question. There's a system to your means of gathering information that would be systematic. Multi-stage is just a way of saying two or more of those methods combined. Okay, now let's talk about bias and sampling error. So again, bias is errors in the sampling method, which is what we kind of just talked about here, or in the sampling design. So bias is when like you screwed up in the physical construct of things, and a sampling error, that's not really an error, so to speak. So again, we'll talk about different forms of bias in just a second. The word sampling error is another way of saying sampling bias. In other words, if you were to draw different samples from a large population, there will be natural variation among each sample, and that natural variation is actually called sampling error. Okay, now types of bias. So again, non-response, that's when a large amount of the population fails to respond. So maybe they don't feel like responding. Maybe you're trying to get an opinion on what someone feels about the Second Amendment, and maybe there's a lot of people who are opposed to it or for it, but they just don't feel like answering your survey, or they don't. So that would be non-response. You're not getting their opinion heard in your survey. Voluntary response is sort of like that as well. Non-response bias is a type of voluntary response bias where, I'm sorry, other way around. Voluntary response bias is a type of non-response bias. I'm sorry, I misread what I was looking at. And voluntary response is when individuals can choose whether or not they want to respond. So again, non-response bias is the idea that a large amount of your population just hasn't responded, whether it's because they just weren't able to or they voluntarily chose not to. That's the difference. So again, voluntary response would be like if someone said, "How's my driving? Call this number." Well, maybe you think their driving's terrible, but you just don't bother to call that number. You've chosen not to call, therefore they're not getting a real idea of what their driving is like. All right, undercoverage, that's when a part of the population is less representative than others. Again, with the census right now, maybe illegal immigrants or prisoners or someone who is just not easy to track down, they're not being counted or they're not being represented in your particular sample. Or response bias, that is when there's a problem in the survey design itself. That's when you have like a loaded question. So response bias would be like, what do you think of this crappy cafeteria food that tastes terrible? If you say something like that, you're leading someone with an opinion, and that would be response bias. Okay, this is something we talked about here. And this is just, again, basics of what's the differences between a sample and a population or a model. All right, and it says here, this is important, using sample statistics, which is what this course is all about. We have smaller groups of data. To use sample statistics to make generalizations about a population that can only occur if a randomized, representative sample was chosen to begin with. So again, you can't take it to that next level and assume that your sample is representative of the population unless you've done your due diligence and done a randomized sample from your population. Okay, an important thing here, the accuracy of a poll or survey is dependent on sample size, not population size. So again, you might be surveying a small population, but you have to make sure that you survey enough people, but also not too many people. And that's something we talk about more in the coming chapters, that whole idea of the 10% rule, if you remember. And right here, this is kind of a continuation of that. So some people think you need a big population to begin with, but really you need to have a good sample size from the population. And this is an ice cream analogy if you want to read through it. But that's kind of the gist of sampling. And again, the study guide I posted has a lot of description as well in it, in case this didn't make sense or help. Okay, now what's the difference between experiments and observational studies? So an experiment, everybody, that is when there's a random assignment of treatments to subjects. So you are physically like adding some type of stimulus or treatment to your subjects, and having a control group to compare it to, and you're observing the differences between the two groups. So generalizations and or cause-effect relationships, causal, you know how we say correlation does not equal causation. The only way you could kind of go with that and say there's a causal relationship is if you've done an actual experiment. And again, you see this in the news right now. There might be anecdotal evidence of a drug helping with COVID, or you might see that one sample it worked on. But for you to say like this drug will treat this, I can proclaim that it is a potential cure, you'd have to have done a controlled randomized study. You'd have to do your due diligence and take time and have enough of a sample to make sure your data is valid. And that's kind of where we are right now, where we don't have a true experiment. They're running experiments, but they're on very small sample sizes. So you have to be mindful of that and careful with what kind of conclusions you draw from it. Okay, so everyone, we talked about this kind of up above. You must be certain the only possible explanation for differences in outcomes is due to the difference in treatments. So again, there's going to be natural variation. Like maybe you have men and women, old people, young people. There's all sorts of different things that could have an effect on your results. So if you're really going to say like this drug causes a cure or this food causes cancer, you really have to have done your work. You have to make sure that the differences you're seeing have to do in treatments, like the drug you're potentially giving someone, not due to their gender or some other thing. So the whole point of designing experiments is to find some way to minimize variation as much as humanly possible. So that's why we use a control group. That's a group that's given no treatment. Or a placebo is given, which is a false treatment. So the person may think they're actually getting a treatment, but they're really not. So the idea that you may see people get better from a placebo, even though it is a, like, let's say a sugar pill, it's not even a real treatment, they just think it is, that's sometimes called a placebo effect. This has actually been found in knee surgery, where if you have a torn meniscus, people, and it sounds kind of unethical, like people were given like a false surgery where their knee was cut open, but they didn't actually repair the meniscus. They were just told they were undergoing a procedure and then like had evidence to prove it happened. And the placebo group actually showed to be just as good at recovering from that a torn meniscus than people who actually got it treated. So it's one of those weird things where meniscus tears and knee surgery and that particular injury, sometimes it's not always proven that getting the surgery and like replacing or fixing it or stitching it together really works. So it's kind of one of those unique situations where you might opt not to get meniscus surgery because the placebo was just as effective. Okay, now on to randomization. Again, the whole point of randomizing is to remove any variation. All right, you're trying to make sure that you didn't buy, like maybe you have an inherent bias and you tend to call on like men before women, or maybe you have a tendency to think like older people will react differently to this drug than younger people. Randomization helps avoid that. You may have this unknowing bias in how you're doing treatments or running your experiment. And the ways we do randomization, again, a lot of times if you have to physically do the experiment, you've learned how to use your random number table. Like if 10% of people fall into one category, you might assign numbers 0 through 9. And then if 15% fall under another category, you might assign 10 through, 34 or something like that. So we've done that before. Sometimes they might actually just tell you that randomization's been done to save you the time of physically constructing the experiment. But if I were the AP test this year, which is very unique, and you do have to combine a lot of things, there might be a case where you show that you're able to perform randomization from a random number table and then go and find, let's say, the probability from it. So again, this is on the review. There's a question about using the random number table that they give you to assign values and whatnot. And most of you guys were pretty good at that when we did it during the year. So if you need a little refresher on that, I would consider looking at the Unit 3 review and the key that went with it. Okay, Another thing about experiments, if we have reason to believe there's some issue we cannot control, like maybe there is gender differences and you don't know if men will react differently to a drug than women, or some of the examples you've seen have to do with like a hair treatment. Well, maybe someone who has straight hair and curly hair will react differently, or maybe someone who has color treated hair will have a different effect than non color treated. So you may block, or it's kind of like stratifying, but in an experimental sense. You might block and say, okay, I'm going to separate men and women to begin with. Then I'll do my randomization and assign a treatment group and a control group. But you're blocking to begin with so you can compare those different amounts and not have to worry if variation had anything to do with gender, for instance. Replication, the word replication is the idea that you should be able to repeat an experiment and get a similar conclusion. So replication is used a lot of times in the scientific community where you might run a test and say, oh man, this drug was shown to really help um, with acne or something. Then another person does it and they're like, whoa, I got a totally different response. So replication is the idea that you describe the process, you describe how you did your blocking, how you randomly assign treatments, etc., so that someone would be A, able to repeat your experiment, and B, be able to, again, they don't have to necessarily get the same results. They might get different results. That actually happens very often where you repeat an experiment and get a totally different conclusion. But replication is the idea that you're able to repeat it based on what was described and given. And that's why when we sometimes do our hypothesis testing, we describe everything. And we say the PHANTOMS acronym, and it might seem redundant, but the idea is that a grader or someone trying to repeat your experiment could read it and understand exactly what you're thinking and doing as you make your way through. Okay, moving on. It says here, don't forget to clarify what your response variable is. Again, this is something that we a lot of times do with hypothesis testing, where that's P, that's like the parameter. You're almost saying, I am doing a study to measure this. So if you had to do experimental design and like kind of use the branches that almost looks like a tree diagram, you might want to say something like, I am trying to determine the efficacy of this drug, ahead of time, just so someone who reads it is aware of that. Now, the term blinding, the idea here is that blinding means one or more groups is unaware of who's been assigned treatments. So it says here, confounding or confounding variables can occur if people involved in an experiment know what is happening. Therefore, blinding can be used to make the subjects, those are the people receiving the treatments, technicians, those administering the treatments, or even the evaluators, unaware of which treatments have been administered to which subjects. So you can't have like every single person blind, like you wouldn't be able to analyze your data. But usually like a single blind study, that's when one group is unaware. So like let's say you're giving people a treatment like an injection of a shot, and some people are actually getting a treatment and some people are just getting water or saline injected into them. That would be single blind. The person doing it knows who's getting it, and then they would analyze it from there. Now, let's say the people who are being told to administer these shots don't know either. Maybe they're just like, here's the syringe, this is what you have to inject into patient one and patient two and so on. Then the subject and the technician are unaware. That would be like a double blind experiment. Now, if for the evaluator to not know, that would be tough because they're supposed to be evaluating what's going on. So now an evaluator where they could maybe be blinded in an experiment, they might just see patient one's data and patient two's data and patient three's data and try and make conclusions from it. And they would be unaware of maybe who received what treatment. And that would be a way to keep them blind if that's what they were trying to study. But if they truly wanted to see efficacy of something, maybe they would know who's from the control group and who's from the treatment group, but maybe they would be blind to which particular individual they are examining when they look at their data. Okay, so that was experiments. And observational studies, these are a little bit more like vague. This is where you're not assigning treatments. You're just kind of observing. And it says here, uses an existing situation. So again, you're not really doing the sampling. There's no treatments. You're just like observing something, taking note of it, and drawing a conclusion from it. And again, in the real world, should you ever continue your studies, a lot of times observational studies are used for, let's say, a thesis where you go back and look at data and kind of like analyze what you took from it. Whereas an experiment, this would be almost more like PhD work. That's where you are physically designing the experiment, administering treatments, observing what happened, and analyzing your data. So, observational studies, though, to give you just a general idea, one type of them, a retrospective study, that's a study when you look back on historical data for someone's observations and maybe you draw a different conclusion from it or analyze their analysis. A prospective study would be when you're, identifying subjects in advance and then you watch it unfold. It's almost like a documentary. If I wanted to see the effects of a new curriculum on AP Stats, the students might not know it's a new curriculum, but I'm observing what's happening and taking note of it as it goes through. All right, and then kind of back to that word confounding, lurking, and confounding variables. It says right here, observational studies can at best establish the existence of an association between two variables. So again, this is almost like correlation. You might notice there's something connected, but you cannot say definitively one causes the other unless it's an experiment. Okay, so now it says right here there's three possibilities. So we're talking about heart attack and people who have a certain protein in their blood at greater risk of a second heart attack. And they studied men. Okay, so the situations that could happen is this. Maybe the protein that is in these men is causing the heart attack. Or maybe because their heart was compromised, that's why you're seeing protein. Or maybe there's a lurking variable going on in which there's something about males that we're unaware of, so a confounding variable versus a lurking variable, the difference, let me read number 3 first and then I'll describe it to you. It says here, maybe there some other unknown aspect of the patient's physical condition or body chemistry is causing this second heart attack and producing the protein as a harmless byproduct. So you know what? Maybe there is something going on there that we are unaware of. So lurking is when you are unaware of it. It's not accounted for in the design of your experiment. Whereas, so it says here, lurking variables tend to appear in an observational study because you didn't design it. Like there might be something behind the scenes that you were unaware of when these people gathered their data that could be having an impact. A confounding variable tends to appear in experiments, and what it's saying here is when you do randomization and control groups and treatment groups, you're avoiding lurking as best you can because you're trying to account for all possible forms of variation. However, confounding might mean there's a variable having an impact that we are unaware of. So, sorry, I think I kind of got myself restarted there. Okay, so to kind of explain that a little bit better, let's say you're reading a study and it says there's an association between the number of firefighters at a fire and the amount of damage. Now, if you were to just read that, it might sound like, are there more firefighters there, thus they are causing more damage? And that doesn't really make sense because what's really going on here is that there's probably more people called to the scene because it was a bigger fire. So there's something going on behind the scenes that's causing there to be an association, but it doesn't mean one is affecting the other. Now here, it says a confounding variable. Amazon's offering a special incentive. If you join Prime, you can start your first 3 months at a smaller monthly payment. And they're trying to see if their advertising was successful. And what they're saying right here is, something in the physical design of what they did here. They started a special campaign right around the holiday shopping season. Was it really their ad campaign that was so good that made people sign up, or was it the confounding variable of the time in which they decided to roll out this, new event? So again, lurking and confounding are both things that impact what you're trying to understand. Lurking is something that you're unaware of. Confounding, you were aware it was December, so that is sort of like a potential thing that is affecting what's going on. Whereas lurking, you kind of have to think outside the box and wonder what could be causing it. So again, what it said up here, the idea that confounding tends to appear in experiments, if this were like an AP question, I would feel you'd be asked that, because lurking requires you to literally think long term, or it requires a lot of background knowledge that you might not be aware of. Whereas confounding variables, it would be present in the explanation of the experiment, and therefore you might be able to logically guess as to what a confounding variable would be. Okay, I think I somehow switched these boxes around, but I think we've talked about everything. So again, if you have any questions on Unit 3, the study guide I posted and the answer key that went with it may describe things a little bit better. If you need to just reread this again, it might sink in a little bit. But again, hopefully just hearing my voice and hearing me describe a few things might make it a little bit more user-friendly. All right, thanks everyone.